about understanding the internal mechanism of LLMs. And this is mostly based on a joint work with my former student and my student. So the question about LLMs usually generate a lot of debate on social media and platforms. And particularly, recently because some weird moves by OpenAI and NVIDIA, right? It's quite perplexing. Um, People have like very diverging opinions about some people think there is a genuine creativity in LMs, but many other people believe it is not the case. Okay, so there's even among experts, there's a disagreement to what extent LMs are creative. So a lot of the uncertainty and confusion we are facing um, today about the prospects of LLMs and generative AI is a poor understanding of its emergent abilities, right? People observed that if you keep training the model for long enough or increasing the model scales, then there is sometimes a sudden increase of models' performance measured in benchmark data. And people say, oh, the model is getting suddenly smarter. If we keep increasing the scale, if we keep training, then potentially, it could be as smart as humans. And if you apply this extrapolation, then you might believe that we are approaching AGI. So it's very confusing to understand those phenomena without getting a like a more scientific approach. Of the of much discussion, uh, stands out ICL and COT. ICL is in context learning, and this is a technique where people use to craft uh, formatted prompts, usually including instruction tokens and demonstration tokens, right, to induce models a certain behavior for downstream tasks without ever changing the model's parameters. Um, Chain of thought, or COT, is a prompting and fine-tuning technique where the model is encouraged to generate a sequence of reasoning tokens in a step-by-step manner before outputting the final result, which is very useful for solving complicated mathematical and coding tasks. Usually, if you train the model on a larger scale, you will see that the model can somehow um, um, do well, and um, you can observe SCR and COT. So if you look into the literature, empirical results all look amazing, but there's a huge gap between the practice and scientific understanding. Um, there are many issues. Okay, when I read the paper, I usually observe people making a lot of claims. And sometimes people confuse mathematical terms with concepts from psychology and cognitive science, right? People make, uh, you know, uh, anthropomorphic heuristics without providing solid empirical evidence. So there's a lot of issues. Also, usually the models are used as a black box model. We don't know what's going on internally. When you grow the model size, it's very unclear what the models will behave, right? Uh, there's a lot of AI safety related concern. Also, um, people usually just use the standard benchmarking. Okay, this is really the driving force for deep learning for the past 15 years. But as you make it more and more powerful, larger, it's unclear whether existing benchmark is sufficient to capture the model's behavior. So a good part of academic research is to provide scientific understanding for emergent technologies, which will not only help practitioners, but also inform policymakers and the general public about the potential opportunities and the risks of this technology. So in my opinion, there are three pillars to understanding LLMs. First, generalization. Okay, if you train the model and then test the model on the same distribution. This is usually called in distribution generalization, right? This is really the classical generalization that you learn in machine learning, right? And like recently, people in the literature have been studying benign overfitting and double descent phenomenon. They all belong to in distribution generalization. Of particular interest in recent years is the OOD generalization or out of distribution generation, which means that the test data can be different from the training data. Okay, if you let the model to solve a novel task, sometimes the model perform pretty well, right? So we want to understand under what circumstances the model can generalize to OOD data. Now, this is measuring the data by treating it mostly as a black box model. If you want to open the black box model and measure the internal structure, you can take the hidden states, you can take the model's weights, and you want to understand how does the model encode the structure from the data. For example, how do those models internally encode concepts, formats, and compositions, right? So this is about understanding what the model is doing. Related to both generalization and geometry is emergence. Sometimes you see a big jump in model's accuracy. Okay, then you say, okay, there's a emergent phenomenon about generalization behavior, but we also want to ask whether there is corresponding changes in the model's internal structure that corresponds to such sudden changes. So there has been a lot of experiments about OOD generalization. I want to first give you some evidence that in some cases the model is actually doing OOD generalization. The first task I'm presenting you here is called symbolized language reasoning, which is inspired by some of the previous tasks. It includes two kinds of subtasks. The first is indirect object identification, very simple language task. If you consider the following prompt, right, then Henry and Blake had a long argument. Afterwards, Henry said so a natural continuation of this sentence is Blake, right? This is something the model is perhaps has seen during training. To make it a bit weird, because we want to construct OOD data, you can do some tricks, to modify the prompt. So the symbolized version is the one we consider, where we replace the names Henry and Blake by some arbitrarily chosen symbols. Okay, so we use the symbols to replace the names, and then we use the same sentence, and then we want to see whether the model is able to figure out that the natural continuation is the second set of symbols. So the next subtask is a special format of in-context learning. The first sentence for ICL is a very simple, normal looking prompt. It's basically classifying an object into three categories. Baseball is sport, celery is plant, sheep is animal, volleyball is sport, lettuce is. If you use this prompt, you want the model to be able to figure out that you want to basically classify an object into one of the three categories, right? So the correct answer should be plant. Now, if you want to make it a little bit weird, okay, you can similarly replace the category names by three sets of arbitrarily chosen symbols. Okay, then we hope the model can continue with the correct label. Now, we can do a very simple experiment. What we do is to have a pool of different names and objects, right? And then we draw 100 test prompts for each of the two subtasks. Okay, we keep the model's parameter the same. We just do a forward pass. This is standard inference, and then we test each subtask with two versions. One is the normal prompt, another is the symbolized one, and we use the symbolized one as a way to test its OOD behavior. So the IOI and ICL have two different formats, and we calculate the accuracy in the multiple choice form. Basically, for the first subtask, we are comparing whether the probability of outputting the first name is bigger than the second name. And for the second subtask ICL, we are checking whether the model predicts the correct label with the highest probability. So the baseline accuracy is 1/2 and 1/3 for the two subtasks. So you can take pre-trained LLMs, right? And then you send 100 test prompts to the LLMs, and then what you get is basically perfect accuracy on the normal prompts. So the models have been trained pretty well, so it's able to get perfect accuracy on the normal prompts. Then you're looking at the symbolized prompts, right? The accuracy is also not bad for the two subtasks. So for IOI, it's almost 100% accuracy. For ICL, most of the models are also doing pretty well. Okay, I think the average is something like more than 80% accuracy. So this suggests that the model is indeed able to generalize to OOD data, although maybe not perfectly, right? It has the ability to do some kind of OOD generalization. So this is a very simple task inspired by people from NLP. Okay. Then the second task, I want to be a bit more controlled. Okay. I want to consider training a transformer, smaller scale transformers from scratch using synthetic data. I call this learning copying with a simple transformer. So the goal is to predict basically complete the pattern in order to copy something from context, right? The model is given a stream of tokens and it contains ABC. Okay, then given A and B, a natural continuation is to predict C, right? This basically completes the repetition pattern. So in the experiment, what we did is to draw IID tokens from a power law distribution, okay? And this forms a noisy background. You treat this as irrelevant information. On top of that, we're going to plant repetition substrings. Okay, so what do we do is to first sample a segment length L, which ranges from 10 to 19. Okay, this is the length of the substring. We're going to plant this substring randomly in a input sequence of length 64. Then we are going to place another copy of the same substring in a random non-overlapping position. Okay, and you treat this as an entire input sequence. Then you're sampling many input sequences of this format, right? And you're going to train a transformer, smaller scale transformer on this type of data. And the goal is to see whether the model is able to continue the repetition pattern if you evaluate the model on those tokens. So this is the data generation scheme. In order to test the model's OOD generalization behavior, we generate data according to a different token distribution. So the marginal distribution of the sequence is different. It's now changed to a uniform distribution, and the length of the repeating substring is increased to 25. Okay, so in literature, this is called a length generalization. To have a minimum experiment to showcase the phenomenon, we trained a smaller scale transformer with only 2 self-attention layers and a single head. So there's we try 2 versions. You can include both. You can both include MLP layer in the middle, or you can even remove that part. We use the standard architecture with a residual connection, layer normalization, rotary positioning embeddings, dropout, and so on. Everything else is pretty much the same. And we train the model on fresh sample setting, which is for each batch, you draw the samples independently. Okay, and we train the model, in a standard autoregressive way. So it's very simple for simple data, but it's challenging in the classical setting. And this is what we got after training the model for 20,000 training steps. Okay, so if you look at the solid curves, I'm making two curves here, right? A blue one and a red one. So those are the two test errors. One is tested on the test data of the same distribution, right? Another is the testing the model on OOD data. And you can see that there's a sharp transition in the model's testing errors. There are two phases. The first phase is weak learning. In this phase, the model seems to have learned the unigram information, which is the marginal distribution of the token. But that information cannot help the model to generalize to a different token distribution. That's why if you compare the blue and the red curve in the beginning, okay, the model, the test error has a dip, right, in terms of the in distribution error, but the OOD error is trivial. Okay, it hasn't learned anything useful. However, around 2,000 training steps, there is a sharp decrease in both test errors. So that means the model seems to have captured the rule of copying. It's able to generalize on both in distribution data and OOD data. Now, I'm also plotting the dashed curves, and they are one layer transformer. We are testing this just for comparison. If you compare the dashed curves with the solid curves, you see a huge difference. For one layer transformers, even after you train it for 20,000 training steps, the errors sort of remain very large. Right? Instead, if you have a two-layer transformer, you have very good performance on this data set. So you can see there's a very distinct difference between the two phases. So this is an evidence that the model can do OOD generation in this setting. And the goal of this talk is to have a better understanding. So far, we learned from these simple experiments that there is a benefit of composition in the model structure, right? If you have two self-attention layers, it's better than one for the copying task. There's an emergent phenomenon, and OOD generation is reasonably well for the two tasks. One is synthetic task, another is a language reasoning task. So we want to get better understanding mostly through experiments. I won't be touching theory for this talk. Any questions so far?
So, so the one layers are just flat, so they're not getting any improvement in care.
Yeah.
And then, why do you think the OD one is like higher and then drops lower, but the IV one is lower and drops and it's not as high?
Yeah, so that's a great question. For the OD data, the repeating substring has a bigger length. It's the length of repeating segment is changed from something ranging from 10 to 19 to 25. So this sort of increases the signal strength in the input sequence, and this is why the model can have a better OD generation accuracy. So when we change the, did you have something?
More training steps before it starts going down or something. Is that we don't necessarily understand that though, or?
Yeah, so in the first weak learning phase, what the model is doing is to learn the marginal distribution of the data. It's looking at the whole input sequence, but it's not able to capture like the interaction between the tokens. It's only using the unigram information, right? And that's why all the error stays flat. But the in-distribution test error is able to do something, right? If you use the margin distribution, unigram is doing something. Okay.
I treat the OOD generalization here as the model learning some robust algorithms that captures some hidden structures within the data.
Yeah.
But it's not dependent on the actual tokens or the distribution of the input data.
Yeah,
that's a more high level view of the data.
Yeah. I'll get to that point. Yeah.
But there's still some kind of like distribution here because you always like recognize your input to be some kind of like A and B as an argument, and then B say to A. There's still some similar structures.
Yes. That's correct. Yeah. I think I'll get to that point later in this talk. But that's a great question.
Does the training loss curve look like?
The training loss.
Yeah.
So I don't have in this talk. There's also a change around that threshold. Yeah.
It's different than the grokking thing where the training loss is 0.
It's different. It's different from grokking because we're in this fresh sample regime. We are not having a fixed training set. In the grokking paper, they have a fixed training set. So we are, in order to avoid, this is also a very good question. People, to give you some background, people about 5 years ago wrote a paper from OpenAI. They call this grokking. Basically, if you train a small transformer or similar neural network on arithmetic data set, right? Sometimes you see that the training accuracy goes to 100%, well before the test accuracy goes to 100%. But in that setting, the training set is usually fixed. It has a very small sample size, and the setting here is different. But I think it all points to some like optimization related structure in the training process. I guess I don't know if I'm going to talk about this if I have time, I can return to this point. So that's a good question. Okay, so I think maybe most of you are familiar with transformer, right? So let me give you a very quick overview. I mean, if you haven't known the internal structure, it's very simple. Okay, if you have a string of, usually a string of text, right? But the first step is to usually convert the text string to a sequence of tokens. You can think of each token as a unit in the vocabulary. And then you're going to embed each token with a numerical vector, okay? Usually also you want to encode position information, right? For each position of the token, you also assign a numerical vector. And then in the original paper, you add the two vectors. So that's the input to the transformer model. And then you're going to process the sequence of embedding vectors through many, many layers. And on the top, you have a sequence of final embeddings. You're using the final position, right? It's a vector of the same dimension. You're using that to pass into a linear layer and then a softmax, which gives you a probability vector. You use the probability vector to do sampling to generate tokens, and that's really the high level view of transformer. So I want to present a sort of non-standard but insightful way of thinking about transformers. Okay, you can think about the input tokens or embeddings, right, as a matrix X, which is basically stacking all the vectors into a matrix. So T is the sequence length, D is the embedding dimension. And for each layer, the self-attention is doing the following things. first you're keeping a copy of the input embeddings or hidden sets from previous layers, and yet you're adding something on top of that. What you're adding is calculated from many different attention heads. There are edge attention heads in each layer. And for each attention head, first you're calculating some kind of a similarity score based on a quadratic form, right? You're calculating X, W, Q, K, J, X transpose. This is capturing how similar two positions are in a given input sequence. Then you use softmax to convert that to weights, right? Probability weights. You use that to do a weighted linear combination before outputting that information to the residual stream. So the mechanistic interpretability literature sometimes views this part. They call this a QK circuit, which is responsible for reading information from the string. Heuristically, X keeps information, semantic information, and many other information about the input sequence. And the QK circuit, which is something you can compute inside the softmax, is capturing that information. Then after the softmax, each attention head is responsible for writing the information to the residual stream. So it's a very heuristic argument, but people have been using this argument in the interpretability literature. So you can roughly view each attention head as a reading and then writing circuits. Okay. So I think attention heads, if you know transformer, I think you should know what this is. It's basically building association between a pair of tokens. Now, there's a long history of interpretability well before transformers, right? So in the pre-transformer age, people in NLP started with word embedding. So what is word embedding? It's very simple. You don't need a neural network. You just embed each word as a numerical vector. Okay, and then hopefully the numerical vector representing each word captures the semantic structure of the word. So in the pre-transformer age, people actually use some very simple methods to embed many different words, and they discovered that the word embeddings can capture rich semantic meanings. For example, there are some plots I'm taking from the papers, highly cited papers. Basically, what the figures represent is that there is latent factors, right, captured by the embedding word embeddings. You can decompose the word embeddings into some directions, and each direction may represent a semantic meaning. For example, the blue curve, the blue direction represents gender-related concept, and the red direction represents plurality, right? You go from king to kings or queen to queens, something like that. So there's a large literature on factor models, on latent low rank modeling. So this is something we already know, well before transformers. In the transformer age, there is sort of an extension of this heuristics, and this is usually called the linear representation hypothesis. It's basically saying that there is a large collection of vectors that represent base concepts. And if you look at the embeddings in the transformer, they're really a sparse linear combination of base concepts. So this is widely observed in many settings. And to give you an example, if you want to look at how Apple is represented by a model, maybe in a sentence, then sometimes you can find base concepts. Each base concept is pointing to one direction, and the Apple embedding is then sort of a linear combination of those base concepts. Okay, so this is a sort of useful concept. You have been using this to do model editing, to do model steering, and so on. This all boils down to finding the right direction so that you want to move the embedding towards the right direction. Okay, so there's also a line of research by Anthropic and OpenAI on linear representation hypothesis. I also have a paper, probably don't have time, but you can use factor models to extract harmful and toxic factors and then directly edit the model to remove the harmful information. So I'm going to explain, okay, from this point on, I'm going to explain why we see the model is able to generalize to all the data, why we have this emergence phenomenon. So back to the synthetic experiment, we want to understand why the model is able to do copying. Recall that the two-layer transformer can be written as a composition of two self-attention map, right? So it involves two sets of parameters, W and W tilde. W is from first layer, W tilde is from second layer. And if you look at the first layer and the second layer, you realize that what's going on in the first layer will be passed to the second layer, right? I don't have a pointer, but the result of this part will be incorporated in the calculation, the QK calculation in the second layer. So a natural way to do some quantitative measurements is to check how well the WQOV matrix from the first layer is matched to the WQK matrix in the second layer. Okay, so here we're taking measurements in the following way. First, we look at a diagonal score, which measures the normalized average diagonal entries of the WQK tilde matrix times WOV matrix. So to remind you, WOV is from the first layer, WQK tilde is from the second layer. So the writing component, OV, and the reading component circuit from the second layer. We want to understand how those two matrices are sort of matched, right? To this end, we take the product of the two matrices, and then it's a D by D matrix. We're looking at the average diagonal entry and normalized by the overall standard deviation. Okay, we want to see how much deviation the diagonal entries from the rest of the entries. This gives us the middle plot. So the left plot I'm just copying from the previous slide. The middle plot is the diagonal score. Then the second metric I'm using is a subspace matching score. What I mean by subspace matching score is by looking at the two matrices, WOV and WQK tilde, I'm calculating the principal subspace of the two matrices. For WQK tilde, I'm calculating the right principal subspace, and for WOV, I'm calculating the left principal subspace. And then I'm going to calculate a generalized cosine similarity. So this subspace matching is essentially, I mean, if you have two vectors, then this is really the cosine similarity. For subspaces generalizing from vectors, you can also define similar matching score. Okay, so if you look at the score, it sort of starts from something near random initialization, and then there's some weird optimization going on. Then there is the jump in terms of a score, which matches the model's generation behavior. So you can also look at the attention pattern, right? Here I'm looking at the previous token head, PTH, or induction head, IH. PTH is from the first layer, IH is from the second layer. So remember that we have two layers, each layer has a single attention head. And I'm trying to understand okay, how the two attention matrices look like over the course of training. So what happens is the animation you see here. In the beginning, there's basically nothing interesting going on. Okay, let me see if it's let's wait a few seconds. Okay, for the animation to end. So here the left is the previous token head, right is that in the beginning, okay, nothing interesting going on. Around the phase transition threshold, what happens is that the model suddenly learns previous token head in the sense that the attention head attends to the previous token. If attention head attends to the previous token, then the attention matrix will be similar to a diagonal matrix with offset 1, right? This is how the matrix is looking back at the previous token. Correspondingly, if you look at second layer, what's going on here is that the model is if you're seeing at this token, then the model is attending to the token right after the identical token in the previous context. So this is how the model is doing. It's combining the previous token head and induction head in order to solve the copying task. So if you think about that, previous token head only depends on position information. It's still there if you change another input. So it completely disregard the token information. It's purely based on position information. On the other hand, the induction head is based purely on token information. Okay, so it's trying to match which token, identical tokens in the prompt. So basically, you need the two complementary layers. They're playing complementary roles. They're sort of composing the position information together with token information in order to learn how to do copying. And this mechanism is quite robust in the sense that it generalizes to all the data. So this is the mechanism for solving copying, and we have seen sudden change clear phase transition, subspace matching, and then we also investigated the role of the pool of copying pattern. There's also a phase transition phenomenon. So I think I'm losing some time. So let me be a little bit trying to speed up a little bit. So you might wonder, okay, this is a very toy example, right? How does this insight translate to realistic LLMs? Okay, so what we did was to do ablation studies or intervention experiments on pre-trained LLMs. For large LLMs, there are many layers, many heads. Okay, what you can do is to basically understand what each attention head is doing in terms of copying by ranking the attention heads on inputs with repetition pattern, and then you're ranking those attention heads according to the attention matrix. And then here we are basically selecting top 50 attention heads as potential, people call this induction heads. Okay, this is originally from Anthropic's post, induction head. We are ranking the attention head in this way, and then we are going to remove attention head from this list one by one and see what's going to happen to the two subtasks, indirect object identification, as well as in-context learning. So you will see the following 4 plots. The left 2 are for IOI, the right 2 are for ICL. So what happens is that for the normal prompts, if you remove induction heads, which are used for copying, the accuracy won't change much, right? You can compare the accuracy with randomly removing some attention heads in the model. The model is still able to complete the normal prompts pretty well. But if you test the model on all the prompts, the prompts with names being replaced by symbols, there is a significant decrease in the model's accuracy. What this means is that the model is likely to solve the normal prompts by just memorizing, the natural language related information. But in order to solve OOD generalization, in this task is understanding what the symbols represent, right? It needs induction heads, because if you get rid of induction head, the accuracy just will suffer. So this is something we get from the experiments. So we draw the conclusion that OOD generation depends crucially on induction heads for the task we considered. And we also considered experiments on chain of thought reasoning using GSM AK dataset, which is a simple math dataset, and similar things happen. Okay, if you remove induction heads, chain of thought won't work. There's a significant decrease of accuracy compared with randomly removing attention heads. So it seems that induction heads is really crucial for generalization OOD and for its reasoning abilities. So we also examined the results across many different LLMs. We look at over 10 LLMs, and they all seem to support the conclusion. We also had some scaling experiments. So I don't have too much time left. Sorry for the interruption in the beginning. So to explain what's going on in the realistic LLMs, I'm proposing the common subspace representation hypothesis, which can be thought of as an extension of linear representation hypothesis. If we have multiple layer, multiple heads, so how do the models generalize? We are proposing the following idealized structure. There is a common subspace, okay, which we call bridge subspace, that encodes the information about composition in the transformer. What that means is that if you have multiple layers, then the early layers will have WOV matrix, which are getting matched to some WQK matrix in late layers. You might identify multiple OV matrices from early layers. You might identify multiple QK matrices in late layers, and they're all matched to the same common subspace. So this is a sort of an extension of a linear representation hypothesis. But in this case, we are not using linear subspaces to encode concepts, but rather to encode compositions. Okay, the reason we propose this structure is that when we examine the pairwise subspace matching, we saw a large trend if you plot the histogram, where the previous token head and the induction heads are getting matched more often than random pairs. So in order to verify this hypothesis, we did some simple verification. What we do is to sort of estimate the common bridge subspace by selecting relevant attention heads, right? You can extract the WQK matrix, and then you pull those matrices, and then do a singular value decomposition to get a rough estimate of this bridge subspace. And then you're going to do intervention experiments. Okay, what you do is to project the weight matrix in the model to the subspace using VV transpose. Okay, it projects to the bridge subspace. You can also do the opposite. You can project each WQK matrix to its orthogonal complement. And you're going to see that as you vary the rank parameter in V, okay, the model is initially, if you do 0, right, it's removing all the information, the accuracy is 0. But as you increase the rank to about 50, the model's performance is recovered. And you can do the opposite. If you start from not doing anything and then gradually removing the information, the model's performance will decrease. So this suggests that there's indeed a common bridge subspace for for copying and for in-context learning. So this is what we examined on GPT-2. We also examined this structure on other different LLMs. So let me give you a sort of speculative takeaway message. So in the literature, it's known that concepts are represented as vectors or linear subspaces, right? This is a linear representation hypothesis. And I'm proposing that if you want the model to compose different, different structures or concepts or skills, there exist rule-based subspaces that connect different layers. Similar to the experiments I show, for copy and for in-context learning, I'm proposing that there might exist rule-based vectors or subspaces that are critical for the models to solve compositional tasks. And this is really the magic for the models to generalize to OOD data. So this is really all I want to talk about. Yeah, thank you. Any question from the audience?
Yeah. Very nice effective for the presentation. So maybe the in-context learning and the old language is our study the mechanism of the attention model. And in some experiments, you remove the NLP layers. I wonder if NLP layer has anything to do with this whole generalization, or they're just intended model that help us understand.
Yeah, that's a great question. In the experiment, synthetic experiment, we didn't include MLP. If we include MLP, we also observe similar phenomenon, which you can find in the paper's appendix. So why do people include or not include MLP? So the basic intuition is the following. People believe that the MLP is encoding static knowledge because it's not attending to different position, right? It's, for each position you have embedding vector, and it's going through some nonlinear function. And people actually, there is some like interpretability papers which examine the structure of MLP, and people say, oh, this basically represents some static knowledge. So for this particular task, copying, we don't need a separate knowledge, related component to solve this task.
How about the really subspace hypothesis page? The J and K in this case,
Yep, there exists a set of K and a set of J, so that you have this match. I think the basic intuition is the following. If you have a large LLM, it has many different attention heads. Okay, some of the attention heads are doing something. Some of the attention heads are doing some other stuff, right? You can identify related attention heads that share this structure. So this is if you have a different task, maybe you have a different bridge subspace connecting different sets of weight matrices.
So then in the experiment you did, what were how did you test these this across all of the layers, or you tested combinations, or?
Yeah, so we examined all the attention heads, and we are applying this projection on about 50% of the related attention, and see whether those edits would affect the model speed. It's not on particular layers, so sort of most of the attention heads in the transform.
Sorry to interrupt. We have a class we're starting in here right now.
Thank you.